Hello, everyone, and welcome to a special Halloween edition of Coffee with Caleffi. So we have an exciting topic today. We're going to be talking about pressure reducing valves in plumbing systems. If you want to go ahead and advance to the next slide there. I think I've got kind of an AV issue here. Bear with me. We're very excited to go through this topic today. We're very excited that it's Halloween, and we will be keeping it very lighthearted today as we go through this topic. We have some frequently asked questions here. If you lose audio, just log out, log back in. That's probably the best way to go if you're looking for the presentation. Select yes in the post-webinar survey, and then we'll also put this up on YouTube later today. All right, certificate of attendance. If this works in your jurisdiction, we will have that at the end of the webinar. You can submit that to your authority having jurisdiction if that works for wherever you may be. I'm happy to provide that certificate. Hydronics 34, breaking news right now. I'm going to put this in the chat. Hydronics 35 is up as of 15 minutes ago on hydronics.caleffi.com. So I'll put that in the chat in a second as we get started. And then we'll mail the physical copies in the next couple weeks as we get that back from the printer. But that's going to be a good topic, evaluating existing hydronic heating circuits. Another one that we wanted to do, that this is kind of a new addition to the Coffee with Caleffi series. So we'd like to, at the beginning, if anybody on the call has a recommendation for anything like this, we'd like to just give an industry shout out at the beginning. This is a great series of books that is produced with ASHRAE. So Danielle Pasig, I am always going to struggle if I say it like with the Italian pronunciation, or like how we would say it in North America. Pasaglia would be closer to how they would say it in Italy. She wrote this really cool gift idea if you're looking for something for a kid in your world that explains kind of engineering and why it's important. So that's a great book. I'll put a link to that in the chat as well as soon as Cody gets going with the slides. But thought that would be a cool thing to mention pre-season here for any gift giving that you're doing. Next month, you are so lucky to have me, the Halloween cowboy, to come back to do the next presentation on hydronics separation simplified. This is going to be kind of a different approach to this topic. We've talked about this a bunch of times over the years, but what we're going to do is kind of a train the trainer version of this. So it's going to be a basic level class for anybody who is new to the industry. This would be a great one. And also, if you have any other ways to explain these concepts, what we're going to do is kind of keep an eye on the chat. And if you want to pitch in with a way to explain how an air vent works or explain what happens when it goes wrong, we'll read some of those comments as we go. So we'll make that interactive for the advanced audience as well. All right. And today we have a Western theme that's going to continue as well. I'd like to introduce our co-presenters, the Director of Product Management and Tech Support, Wilbur, and we also have the National Training Manager, Mr. Ed, is here with us today. So thank you, thank you, Kevin, Freidt, and Cody Mack. You can take over from here, and I will keep working on my facial hair and be watching questions in the background here. So take it away, guys.
Perfect. Thank you, Max. That is one beautiful mustache you've got there. Welcome, everybody. Happy Halloween. Happy Thursday. And I'm going to take this thing off because it is very hot in here. So give me 1 second. Woo. All righty. Now I take that off. I find it ironic. I look like the other end of the horse. But anyway, so let's move it along here. We are going to be talking about pressure reducing valves in plumbing systems, right? And so for today's topics, you probably read this in the description for the actual webinar when you signed up. We're going to talk a little bit about when you need a PRV, how they work, and they're pretty simple devices, right? But they can go awry if they're not done properly, So from there, we're going to talk a little bit about how a PRV can help control operating costs, and we're going to talk about sizing them and what happens if you don't size them properly. And then from there, we'll talk about different applications in series or parallel, and different applications in like single family versus multifamily or mid-rise, high-rise type buildings as well. All right, so From there, if you guys do have any questions, obviously don't hesitate to type them into the chat. I see one here already. I cannot hear the presenter. I am not muted right now, so if you can't hear me, definitely just log out and log back in. Will probably be your best bet there. So we'll dive right in here. When do you need a PRV? So a PRV is a pressure reducing valve. So it's kind of pretty self-explanatory. It's a valve that reduces pressure. But when we talk about why we would need to reduce pressure, the simplest one right off the bat is going to be the fact that most of us are abiding by codes that require it. And not only do they call out very specifically 80 PSI, but in that, they also call for a pressure reducing valve and sometimes even a strainer if your pressure is exceeding 80 PSI. So right off the bat, we've got IPC, UPC, and the state of Wisconsin, where we are based out of in Caleffi, North America. Again, 80 PSI is going to be your ticket. There's a lot of information in there about minimum pressures as well, depending on the types of fixtures and things like that that you have in the building. But obviously for today's webinar, we're really more worried about excessive pressures, not necessarily those low pressures. So how do we end up with high pressures in residential, commercial, any of these buildings that you might have, right? So some potential causes for excessive pressure, first is going to be elevation. And what we're talking about here is the difference between where the water is stored versus where the water is used. And when you look into some of these places around the world where, you know, you've got water towers at a high point, and again, elevation, you've got somebody way down at the bottom of a hill, you've got this ability, this potential for incredibly high pressure due to the height difference there. And, you know, just kind of the basic math here is going to be 0.43 PSI per foot. And you can even see in the elevation or in this illustration here, you know, you've got 100 feet worth of distance from one residential home to the guy at the bottom here, right? And you'll notice it actually went up 43 PSI, and that can be pretty substantial. But the other thing that we're seeing, even in areas in the central United States, where, you know, we have pretty flat regions, right? I was in Quincy, Illinois, for example, a handful of years ago, and I always like to ask this question, and you guys can feel free to jump it into the chat here too, into the questions pane. I always ask, what's the highest pressure you've ever seen to a residential or commercial building? And, you know, it's pretty common. We'll see, you know, 90 to 100, 120 sometimes. But even in Quincy, Illinois, which again is probably one of the flattest areas in the country, they were seeing 125 PSI into some of these buildings. Now, the other thing I always like to mention, especially to the residential contractors that might be checking homes during the day, okay, as they're checking homes and they're checking the pressure coming into these homes, you got to remember that the pressure at that time when they're there is not going to be the same pressure as what you're going to see during non-peak times, and let's say in the middle of the night and things like that, right? And so I always encourage those contractors to put on one of those gauges on a hose bib with a lazy arm or a lazy hand that will register your peak pressure by the next morning, and, you know, leave it there overnight and just see what happens. Because a lot of contractors will see that it's 75 PSI and they'll say, hey, I'm perfect, right? I don't need to put in a pressure reducing valve, but it's 75 PSI during the day, not necessarily at night. And so we need to make sure that we're under that 80 PSI, regardless of its elevation or, again, the flattest parts of the country. So another good reason is going to be because of boosted systems, right? So in order to get pressure to the highest points of a building, whether it be mid-rise, high-rise, whatever, typically if you're going more than 5 to 6 stories, you know, you're probably looking into a booster system. And so as you look at this example on the right-hand side here, you know, we've got a 30-story building, and in order to maintain a static pressure of 35 PSI at the very tippy top of that building to make sure that your flush valves work and things like that, you need to boost up to 180 PSI. So with that 180 PSI, obviously we can't use that at the fixtures in the lower floors. So we are going to have to reduce that down in those particular areas to maintain a safe pressure for those fixtures. And as you can see on the left-hand side, our model, I believe that's Mr. Chris Swade. If Chris is on today, he can comment whether that's him or not. But one of our reps there in the Chicago market, they're actually setting up and starting up a booster pump system there.
Hey, Cody, we got a comment that the domestic water pressure in downtown Kansas City is about 120 PSI. So this viewer said they didn't need a booster pump for a 9-story building. So
wow.
That's, yeah, even in the places that aren't mountainous or whatever, it can come up. So yeah, that's
I think
odd
120
example.
psi. I think 120 psi is enough to blow that fake mustache right off your face,
I
even if
think so,
if
yeah.
you got it in the right direction, you know. But yeah, so I mean, it's pretty crazy. So yeah, I mean, it's definitely, again, even in the flatter parts, you know, you're going to see that quite a bit versus that picture that we were showing before. I believe that's Colorado. But again, it just depends on where the water is being stored and where you're using it in a lot of cases. But sometimes we're just distributing high pressure like that to try and get out to those far-reaching areas and suburbs. So when we talk about problems created by high water pressure, right? You know, the first one that comes to mind is going to be stress on piping and fixtures. You can see that picture on the right-hand side. Obviously, your flexible braided type hoses and things like that, your washing machine hoses, even your flexes running from your stops to your fixtures, are going to be some of the most susceptible, especially washing machine hoses, right? And so when you put high pressure on those devices and you do have a failure for whatever reason, you are going to have issues, and it's going to lead to, you know, insurance claims and all kinds of things that we want to try to prevent, right? And so from there, high pressure can also lead to water hammer type events, and more importantly too, it leads to a lot of water waste, and this is really important in areas that are more drought stricken, like the southwestern parts of the United States, California, Southern California, things like that. You know, to where if we can control that water pressure, we can control some of the consumption in those buildings, and thus be able to save on water. And so the last one, it sounds kind of silly, but as a quick example, I was in a sporting goods store. It's a national chain type sporting goods store. I had to use the restroom, went to the restroom, and I was taught a valuable lesson that when you turn on the faucet, you stand back as far as your arms will allow you to reach the faucet and still turn it on. I turned on that faucet. It literally sprayed and hit the bowl of the sink and splashed out all over the place. I came out of there. My daughter thought it was the most hilarious thing in the whole wide world. But the fact is you will get splashing up and out of the sink there, and you know there's lots of issues caused by that excessive pressure. Again, one of them being embarrassment. So by curing a lot of these issues, you can prevent, you know, that excess money going down the drain, and you can help control those operating costs, which I think is incredibly beneficial for building owners for sure. All right, so how do PRVs work? Okay, very simple devices. What we're looking at here is going to be a diaphragm style pressure reducing valve, and you'll notice that rubber diaphragm right there in the kind of the middle, just above the pipe connections there. And you'll notice that right above that is going to be a spring, and that spring is calibrated to a specific pressure. Okay, and basically you're going to have two opposing forces here in this particular case, and you'll notice that the shaft and seat are actually sealed up against here, so it's not actually allowing any water flow through. But basically what happens is if the downstream pressure is high enough, it pushes up on that diaphragm, pushing up against that spring to close off that PRV and not allow water to come through. But as the downstream pressure decreases, the spring overcomes that downstream pressure and allows the PRV to open, as you can kind of see in this next graphic here. So again, you'll notice that there's now water flow going through here, and you know, again, pretty simple, but again, you just got a spring, you got a diaphragm, and you got the pressures on either side, allowing water to flow or not to flow. So anything to add there, Kevin, before I move on here to the next style?
Nope, that's all really good.
Okay, perfect,
Good. Yep.
perfect. So from Caleffi, just a quick little, you know, a little plug here for Caleffi. For the diaphragm style pressure reducing valves, we actually have our 533H and our 535H Pretal. And so these are going to be our diaphragm style pressure reducing valves. And I just noticed with one of the questions that we had here today, one of the questions was, do PRVs work on static pressure or just dynamic pressure? When we're talking about setting these PRVs, setting it to whatever pressure you desire, that is going to be in a static condition. These are all direct acting pressure reducing valves, again, with that spring and diaphragm and everything like that. And during a dynamic condition, you will notice that you will have what is referred to as fall off pressure, but we'll get to that in a little bit. So it's a great question though, because again, this is something that does come up. I've had customers call me and they're running faucets and trying to dial in the pressure reducing valve, and it's just not quite how that works. So again, you're setting it based on a static condition, and you know, during a dynamic condition, you will get fall off pressure. So from there, we're going to have our piston style pressure reducing valve. So you'll notice that in the middle here, that instead of having a diaphragm, we actually have that solid piston with rings on the side of it, just like an engine in a car, right? You're going to have pistons with rings, and those rings are there to seal off from the area with the spring versus the area with the water. And you might think to yourself, why on earth would I want to use a piston style PRV over a diaphragm style PRV? Well, piston style PRVs are just a more robust pressure reducing valve. This is a valve that is going to be perfect for applications that experience lots of water hammer. So think of applications like irrigation, or laundromats, or anything with a lot of fast acting solenoids, that might be like dishwashers and things like that, where you might see excessive water hammer. They're going to be able to hold up under those harsh conditions. Now, with piston style PRVs, they are slightly less accurate in some cases versus a diaphragm. A diaphragm style PRV is very accurate. Piston style PRV will be slightly less accurate, but again, it makes up for it with that robust capability of just dealing with adverse conditions, right? So again, a little plug there for our Caleffi model here. This is the 536 Prescal HP. And we'll talk about this in a little bit, but we actually offer this in two different models when it comes to the setting range. One model is adjustable from 15 to 90, and the other is 90 to 150, but we'll talk about why you'd need one or the other in a little bit there. All right, so moving on from how PRVs work to how do we size them, okay? If I'm talking with a group of contractors, and I know there's a bunch of you on today, which I really appreciate, and lots of engineers too, coming off the heels of the great ASPE show in Columbus. I hope we saw you guys there. I hope you're able to make it, but we've got a lot of engineers on today. But when I talk to those contractors, I always just remind them, and the wholesalers too, for that matter, when we talk about sizing PRVs, it's not just about pipe size, okay? There's many areas, for example, that require a minimum service of 3/4 inch, regardless of how many bathrooms are in a house. And we will actually get calls about how they're having some issues here or there, and we'll actually recommend going to a 1/2 inch PRV. Just because it's 3/4 coming into the house, you're feeding the rest of the house with that 3/4 inch doesn't necessarily mean you need a 3/4 inch PRV. So, but to kind of move on from that, when we talk about sizing, a lot of our water distribution, our domestic hot water, mixing valves, PRVs, all that fun stuff, we're typically doing it off of some version of what we see here, which is going to be referred to as the Hunter's curve. Basically, we're going to apply a weight to the different types of fixtures. We're going to add up all those fixture units, and from there, we are going to take it over to the curves. And you'll notice that there's 4 different curves here, and it's based on the different applications. And a lot of this is based on the probability of multiple fixtures being on at one time, okay? So this was actually developed by Dr. Roy B. Hunter in the 1940s, and you'll notice there's the curve there at the bottom is for office buildings, the next one up is apartments, the next one up is hospitals and hotels, and the last one is restaurants. And so the way I always talk about this is if you have 100 fixture units in an office building, the probability of all those being on at one time is going to be, very low. But if you have 100 fixture units in a restaurant and it's during that dinner rush, the probability of all those fixtures being on at one time is going to be incredible. So if you have that 100 fixture units in an office building, that peak flow rate might be 16, 17 gallons per minute. But if you have 100 fixture units in a restaurant, that's almost 70 gallons per minute. And obviously that's a big difference. But one of the big problems, whether it be the existing, the original Hunter's curve or modified Hunter's curves, or, whatever's been adopted into your codes and things like that, is that they're based on data from the 1940s. They're based on fixtures from that era as well. And obviously things have changed. We've got fixtures out there that are incredibly low flow rates. We're talking about, toilets that are less than 1 gallon per flush. We're talking about recirculating shower valves. If you're really excited about that, you should look it up. The ability to use 80% less water with recirculating the water in your shower, which sounds incredible. But from there, what this usually leads to is a wildly oversized system. Okay, and this is not just pressure reducing valves. This is domestic hot water production, PRVs, distribution piping, so on and so forth. And so how do we get around this? We really don't have a huge, relationship here, but I just always try to bring this up when we talk about sizing things, is going to be, and I hope you guys have seen this before, this is the water demand calculator from IAPMO, the International Association of Plumbing and Mechanical Officials. They have produced this water demand calculator. It's available as an app for your phone. It's available in a format like you see here in a spreadsheet, okay? And basically you are gonna enter in the total number of fixtures along with the fixture flow rates, and you're gonna press that green button and it's gonna give you your peak flow rate or your 99th percentile demand flow, right? And so you might think to yourself, well, I haven't seen this before, and is it applicable to my area? Okay, and this is referred to as UPC Appendix M. Okay, so if you are a UPC jurisdiction, this has also been adopted into the states of California, Massachusetts, and the state of Wisconsin. So definitely use this to your advantage. This can really change how we size up everything in our systems, right? Not just the PRVs, right? But basically, we want to know what that peak flow rate is because we need to be able to size our pressure reducing valve as it pertains to this conversation. But I talk about right sizing our buildings and right sizing our distribution. If you get a chance, we did a webinar a number of years ago. It was kind of a case study webinar, and I think it was a really cool webinar. It was with Gary Klein, and Gary and they basically talked about this existing building, and it was a nursing home facility where they were building an identical one right next to it. And the existing building, Max, do you remember, or Kevin, do you remember, was it 1.5 or 2-inch distribution in that building? I don't remember right off the top of my head.
I feel like it was 2-inch from memory, but yeah, it was a significant.
It's abandoned.
That sounds about right, Cody.
All right, no, that's perfect, guys.
Kevin did not have a costume at the beginning of this webinar, so that meant somebody found him that costume.
He's gonna rob the train. No, so what's hilarious about that though is Max's mustache, but also the fact that with that 2-inch distribution, they actually in the existing building put on data loggers, and they figured out over the span of several weeks the peak flow rate in that actual building was like 9 gallons per minute. So you think about how much everything was wildly oversized. We talk about controlling operating costs. Let's control upfront costs as well. So right sizing these buildings is going to be key. I've talked to a number of engineers that have used this water demand calculator, and I ask them, like, how did it make you feel? And they will say flat out that it makes them incredibly nervous because they're seeing flow rates, like 50%, 40% of what they're normally used to. And I just want to get across here that bigger is not always better, right? So we want to find that peak flow rate. We need to size our pressure reducing valve based on maximum flow. And once we get that peak flow rate, we're going to take it to our sizing charts here that are available in our literature. And you'll notice here in this chart on the right-hand side here that there is a blue shaded area. And when we're talking about our peak flow rates and sizing our PRVs, we talk about this blue shaded area. It's basically velocities between 3 to 6 feet per second, right? And at that point, you can take that flow rate and you can set it in there and basically find the PRV that matches that flow rate that's between that 3 and 6 feet per second. So we have those design flow rates laid out at the bottom here as well. And just as a quick example, if we had 8 gallons per minute, again, this would be, a residential single family style house kind of thing. If you were to take that up there and it would go into that blue shaded area, you would be looking at a 3/4 inch PRV, right? But I'm going to go back here real quick, okay? This water demand calculation was actually done at my own house, okay? And I'm on a private well, so I don't necessarily need a pressure reducing valve. But I wanted to point this out that my 99th percentile demand flow is 6.5 gallons per minute. And if you were to actually take that 6.5 gallons per minute and plug it in here, it would actually line up perfectly with a 1/2 inch pressure reducing valve. And that's a great point to bring up because again, I have 3/4 inch service into my house and 3/4 inch distribution for the entire house as well. So just because it's 3/4 inch or it's 1-inch pipe doesn't necessarily mean that you need that size pressure reducing valve. So again, we're going to size it based on that maximum flow rate or that potential peak flow rate and get it in that 3 to 6 feet per second flow rate or velocity range, and you're going to be good to go there. But the other thing to consider, and especially when you're sizing in commercial buildings and high-rise buildings where you might be, kind of a little critical as far as, the pressure that you'll see coming out of that guy, is what we refer to as fall-off pressure. So as I mentioned before, when you set a pressure reducing valve right off the gate, you're going to set it at a static condition. So you're going to, with nothing running in the house, you're going to try to set that pressure reducing valve to whatever your desired pressure is. And what you'll see, though, is that as you start turning on fixtures, you will run into what's referred to as fall off pressure. And so as a quick example here, you've got that 90 PSI supply with a 75 PSI set point. You turn on one faucet and it doesn't drop very much, maybe 1 PSI, two faucets, 2 or 3 PSI. But then all of a sudden you start turning on that Roman tub. And that's when you're going to start seeing that kind of that dive off a little bit. Not that it's diving off a lot, but it's getting down to 68. And so, that's a drop of, 7 PSI. And that might make a big difference in a commercial building where you might only have 35 PSI. And maybe that's an issue if you're, or if you've got 45 PSI or whatever the case may be, that might be an issue with, again, your flush valves and some of those other devices. So we do also have a chart in our literature. If you do know that peak flow rate, for example, that 8 gallons per minute, you can take it up to the 3/4 inch pressure reducing valve line. You can figure out right off the bat that it's going to be a little over 7 PSI at fall off during that peak flow rate. So it's not going to be 7 PSI every time you turn on a fixture, but it will be 7 PSI when you hit that peak flow rate in your calculations, right? So from there, we have gone through the fact that we need to size these based on the peak flow rate. Maximum flow rate is definitely going to be key. We need to know that right off the bat. But one of the things that's often overlooked with pressure reducing valves, and that can cause a lot of grief, right, is going to be minimum flow requirements. Okay, I didn't know how else to get across the importance of these minimum flow requirements besides just to put lightning bolts in, right? That hopefully this got everybody's attention. But the fact is that these pressure reducing valves have minimum flow requirements in order to basically have stable operation and stable output. What happens if you don't meet minimum flow requirements? You could have chattering and you could have squealing and things like that. And this is all things that we want to try to avoid. Obviously, it's a nuisance to whoever's in the building that has to listen to those noises. It might even sound like water hammer in some cases if the PRV is chattering quite a bit. But it's also going to be hard on your pressure reducing valves. It's going to mean that they are not going to live as long of a life as they could or should. So how do we deal with the fact that we need to meet maximum flows, but what about these minimum flows? How low are they, or how high are they, on the minimum flow requirements? So just as a quick example here, this is going to be an example or an application where we have a peak flow rate of 40 gallons per minute. Okay, and with this peak flow requirement of 40 gallons per minute, we know right off the bat that we're going to need an 1.5 inch pressure reducing valve. Okay, but that 1.5 inch pressure reducing valve is going to have a minimum flow requirement of 7 gallons per minute. And you can't necessarily guarantee that with demand from fixtures because, 7 gallons per minute is quite a bit, right? And so what you'll notice in our literature is that we recommend our minimum flow requirements is going to match up to about 1 feet per second velocity through the pressure reducing valve. So if you're looking in that chart that we showed a couple slides ago, 1 foot per second is going to be that minimum, right? But in the case of the 1.5 inch PRV, the minimum is 7 gallons per minute. And so you'll notice here, we actually added a 3/4 inch PRV into the mix here, and we are piping them in parallel, which is really interesting because this allows you kind of that high-low range of control. And what you'll notice is that in this application, the small pressure reducing valve is set to a slightly higher pressure than the large pressure reducing valve. Usually this is somewhere between 6 and 10 PSI, and it's 10 PSI in this example. And so what you'll notice is that as you start to have demand downstream of the PRVs, the small PRV is going to kick in first, right? Because this guy's set to a lower pressure. But as the fall off pressure, starts to increase on the small PRV, it hits that 10 PSI of fall off. That larger PRV is going to kick in and it's going to take it the rest of the way, right? And so what you'll have here is kind of that high-low capability, and you'll be able to cover those low flows without chattering and squealing and making all kinds of noise and premature failure of pressure reducing valves, and you'll be able to cover that spread no problem. Now, we've also seen applications where they actually do this in kind of a high, medium, low fashion as well, which is pretty unique. But I would say, anytime you start thinking about PRVs, anything over 1.25 inches, 1.25 inches, 1.5 inches, 2 inch, that's when you really, especially with these direct acting PRVs, should be starting to look at, a high, low or parallel type application like this. Anything you want to add there, Kevin?
Well, we really want to encourage people to do this, to not be afraid of it. Go ahead and put this in your designs. Installers, go ahead and install it. It's not that much more, right? You have to just buy one more PRV, but it solves a lot of problems. So
For
this is
sure.
a really good approach for any job that'll have a, kind of a low minimum and then a higher maximum for sure.
For sure. Yeah, and I always joke with the contractors and the wholesale guys, this means you get to sell two pressure reducing valves. This isn't a bad thing. It's proper for the application. You're going to get better life out of the equipment, and you're going to have better control. And yeah, you get a second PRV in the mix as well. So from there, that's how we deal with minimum flow
Hey,
requirements.
Cody, I've got
Whoa, Hulk
a
Hogan with a cowboy hat.
I've got a question. The PRVs, do they need to be installed vertical like that, or could they, or sorry, horizontal, or could they be installed vertical? Does that change any of
Okay,
the
so
operation?
that's a great question. When it comes to orientation of pressure reducing valves, we do recommend if you're putting them in horizontal pipe, make sure that the cartridge or the actual like the valve body is pointing somewhere between the 9 o'clock and 3 o'clock position. We don't want it to be upside down. It's going to basically gather sediment and things like that, and it's going to lead to premature failure. Really, no issues if it's installed in a vertical pipe in that kind of application there. But it's the horizontal pipes we want to make sure that it's somewhere between 9 o'clock and 3 o'clock. So, I love that Hulk Hogan mustache, by the way. That's a good one. So I think there's a brother in there somewhere if you watched wrestling back in the day. But anyways, all right. So from there, the next application or the next interesting one that you might see is series pressure reducing valves. And these are the applications that we'll see if you do have incredibly high incoming pressures, right? So, 125 is not incredibly high. We will, however, see areas just coming in off the street at over 200 psi in some of the mountainous regions where, again, that elevation between where the water is stored and where the water is used is so great, right? So, just as a quick example here, right? You've got 175 psi coming in, and you want to set that pressure reducing valve to 45, and that's an incredibly high ratio, right? We actually have recommendations for about 2 to 1. So if you've got 120 psi coming in, you set it to 60 psi going out, everything's great, right? But we can't do that with one pressure reducing valve. So what we've got here is a scenario where you've actually got two pressure reducing valves in series. And we have 175 psi coming in, 80 psi downstream of that first model, and then from 80 down to 45. Okay, this is going to reduce that stress on the PRV and the squealing that comes along with it. You notice here, I might scream. It's not I might, I will scream, and it will not like it. Okay, so if you do have those incredibly high incoming pressures, you do need to make sure that you're doing these in series like this. But what about if your PRV is higher than your incoming pressure is higher than 175 here, for example? So this 535H that we have here in the illustration, the setting window is between 15 and 90 psi. So theoretically, if we're going to abide by this 2 to 1 ratio, the highest pressure we could have coming into it is 180, which is kind of limiting in some cases because we will, again, see pressures higher than 200 in some cases, sometimes even upwards of 250 psi. So how do we deal with that then? And how we deal with that is with our piston style PRV, the Prescal HP, that has that adjustment range from 90 to 150. So I mentioned before that Prescal HP, the piston style on the left here, this is available in a setting range from 15 to 90, but also from 90 to 150. And so with that 90 to 150 model, you got this example where you can go from 250 psi, setting it down to 120 or 125, and then use the diaphragm style PRV downstream of that to go from 120 to 60, and do this all very precisely. You've got that robust PRV on the front end controlling that pressure, and then you've got the diaphragm style PRV to really dial it in 100%. Okay, and so this is an application that we're seeing more and more of, especially in those mountainous regions. Something to take advantage of here is going to be a new kit that we are actually offering. So for those mountainous regions or those boosted high-rise buildings where you do need to have PRVs in series like this because of the incredibly high pressures, we actually have developed this kit where you've got a small spool in between to keep that, that lay length really short, so that way you don't have to have these big giant access panels and things like that and lots of room. We also have gauges downstream of the first PRV and the second PRV, so you can dial in that pressure easy peasy, right? Lots of different connection options as far as connection types pipes and things like that. But one of the things that you might notice here, you've got the two PRVs in series, you've got the gauges and everything like that, but you might be thinking to yourself, what in the world is that right back there? Okay. Now, what that actually is a device to control expansion. Okay, now what we have here with two PRVs is we've got this first PRV where you've got water coming through, and you got water going through the second PRV. And let's say, for example, that water coming in off the street is 45 degrees because it's a cold climate. It's Denver, it's Wisconsin, it's somewhere north of the Mason-Dixon line, let's just say. Okay, and you've got these PRVs in a mechanical room where it's 90 degrees. Okay, and now all of a sudden you got 45-degree water coming in. Demand stops. Nobody's flushing toilets. Nobody's using the sink or anything like that. Everybody goes home for the day, whatever. And what's going to happen is that 45-degree water that's stuck between these two PRVs is going to start coming up in temperature. And as engineers and contractors, we all know the damage that expansion and high pressures can cause to, equipment and, piping and distribution, all that other fun stuff, right? Now, bear in mind, this is a tiny little bit of water, but the fact is that we need to control that expansion. It can do quite a bit of damage. So we have that little expansion device back there to control that in that particular event. Anything you want to add there, Kevin or Max?
Yeah, we just introduced these as a kit, so you can buy it just like you see it right there, all pre-assembled from the factory. So there were a couple of raised hands.
Yeah, we've got some questions in the
Max, did you
chat
see
as well
those?
about the distance there. So we've got
Okay.
a very short spool piece. What would be
Yes.
the problem if you had 10 inches of pipe there?
Right. Same idea. The more pipe you've got in between there, the more volume of water you're going to have. And just like any expansion tank or anything like that, the size of that expansion tank is based on the volume of water and the difference in temperature that you're going to see. And so if you had a longer distance there, you're going to need a bigger expansion control device. Does that sound about right, Kevin?
Yeah, that's right. So you want to keep it as short as possible to minimize
Sure.
the amount of water that can get trapped in between the two PRVs.
Yep. Perfect. Any other questions that are pertinent right now, Max, or are we going to handle them at the end there?
There are a bunch coming in about that, but I think that covered a couple of them, but I'll keep an eye on
Okay.
it.
All right. So from there, we did talk about how PRVs, sizing them, and what happens if you oversize and undersize. Well, what's more funny than Max's mustache is the idea of anybody undersizing a pressure reducing valve. That never happens. It's almost always oversized, right? You'll get squealing and chattering. And that is a good portion of our technical support calls. If we do take them on our pressure reducing valves, is going to be sizing concerns and the symptoms that go along with it that then lead to a solution that requires resizing or recommendations for resizing. But when it comes to malfunctioning pressure reducing valves, I would say probably the number one reason, that pressure reducing valves will malfunction, right up there with sizing of pressure reducing valves, is going to be dirt and debris. Okay. Now these pictures here are literally the very first pressure reducing valve that we took back under warranty. Okay. Now, as you can tell, it wasn't necessarily a warrantable item, but hey, it got sent back, so we're going to take a look at it, right? And so the comment from the contractor was that, hey, we put this in and we go to leave for the night on this new construction job, and by the time I come back in the morning, it's 90 psi downstream, and I've got it set to 60. It's not holding the pressure that I want. It's going to give me issues, right? And so I took this PRV. I said, hey, send it back. He already had ripped it out, so he sent it back, and I installed this in our lab in Milwaukee. And in Milwaukee there, within minutes, I could see that it was starting to creep up in pressure, right? And the reason being, and you can see that red arrow right there, is you've got the sealing element at the bottom of that pressure reducing valve. And, on the inlet side of that cartridge, we do actually have a screen, a strainer screen that will help to kind of hold back a lot of the bigger chunks, right? But some of the smaller chunks might make it through, and what happens is they get stuck in that sealing element, and then the cartridge can't seal off 100%. And so what happens during long periods of inactivity is that that high pressure starts to bleed by, because it can't seal off 100%. It starts to bleed by, and by the time they made it back in the morning, it was up to 90 psi or whatever the upstream pressure was. Obviously, it's less than desirable, right? And so that's a big issue. So so how do we deal with this? What was interesting about this particular scenario is that, within minutes, I was able to pull this cartridge out. I was able to clean it with a soft bristled toothbrush, and I put it back in there, and the thing worked like $1,000,000, right? Now, on the other end of things, we talk about exceeding pressure because it can't seal right. But what about decreasing pressure? Kind of the same idea, just a different swing of the pendulum, or the other end of the pendulum swing there, is you start to clog up the strainer upstream or the strainer built into the cartridge, and obviously you're going to get incredible pressure drops, right? It's just like plugging up heat exchangers in domestic hot water production systems. It's very similar there. So, I mean, as the flow rates increase, the pressure drop's going to increase, and it's going to look like poor water pressure. And so, again, you can just take that guy and you can clean it right up, right? And it's very, very simple. So I would say, again, when it comes to malfunctioning PRVs, between sizing and dirt and debris are going to be the two biggest ones. And again, I try to ingrain this into a lot of our contractors and building maintenance guys. These PRVs are designed to be serviced. So you can pull that cartridge out. It is one piece. You can clean off that screen, clean off the sealing element, put back in. From there, you can also replace the cartridge if necessary. You can replace that whole cartridge as one piece and get that thing up and running again, right? So that's another one. Now, I would say another good one to think about here when it comes to PRVs not working the way you want them to, or not meeting your expectations, is that excessive downstream pressure on a PRV. And a lot of the questions that we have are related to improperly sized or improperly set thermal expansion tanks for domestic hot water production. So if you do have a pressure reducing valve in a system, whether it be residential, commercial, it doesn't matter, okay? And it's not the pressure reducing valve's first intent. It's not its purpose in life, right? But it does act like a check valve or like a backflow prevention device almost, right? It allows water through, but it doesn't allow water back. And with that in mind, it's going to produce a closed system. And if you do have a domestic hot water production system downstream of that PRV, it is going to need a properly sized and set up thermal expansion tank. And so, obviously, I'm probably preaching to most of the choir here, as we say. But the fact is, I'll talk to a lot of wholesalers and contractors, and I'll tell them, like, hey, if you are replacing a PRV or putting in a PRV, you do need to make sure to have that properly sized thermal expansion tank. Okay, I joke about, do you recognize this bucket here? The fact is without that properly sized expansion tank, that water heater is going to turn on, and it's going to pop that pressure relief valve sooner or later on the water heater, and thus you've got the bucket underneath it to contain the little spitting and splashing, right? Now, I will say in this slide here, there are some pressure reducing valves that actually have a check valve built into them to allow backwards flow. Okay. Some manufacturers tout this as a feature and everything like that, and I can't say that I'm a big fan of it. Okay. There's a couple reasons. One, as water comes into your home or building or whatever the case may be, there's not a single water utility on planet Earth that wants the water to come back. Okay, they want you to keep it. They want it contained in your building. They do not want the water back. Okay, so by having that check valve in there, if the downstream pressure exceeds the upstream pressure, it allows it to travel backwards, right? And so again, the water utility doesn't want the water back after it's been in your home or business, right? Or your process or whatever the case may be. The other problem that you run into is that if you do have pressures upstream, incoming, that are higher than 150 psi, it's not going to work anyways, because if you do have upstream pressures higher than 150, you're probably going to pop the pressure relief valve on the water heater first before it ever has a chance to go backwards. So again, the idea here is that you are creating a closed system. Thermal expansion definitely needs to be managed, and it's done with the properly sized expansion tank. All right, so from there, I'm going to invite my colleague Kevin back on here, and we are going to talk about the different types of applications with pressure reducing valves here. And Kevin, I'll hand it over to you.
Okay, yes, stay there, Cody. We can chat about these. Let's look at some applications, and these are just schematics. They just represent where you might put PRVs, where you won't put PRVs. So this is a very simple low-rise residential, 3 floors. Say that you have your mechanical equipment in the basement down by the supply point, and we show a little water meter coming in from the supply point and one single PRV. So that PRV will pressurize the whole system that you see here. It will pressurize the water heater. That's an indirect tank there that has a thermostatic mixing valve coming out. And the tempered water will go up and service all the hot water fixtures in the home. There's a second or a main floor and then an upper floor there. So if you had that PRV set for 45, just for example, and you had 12 feet between that main floor and upper floor, then up at the top, maybe you would have more like 35 PSI, right? Because you drop about 5 PSI if you keep the math simple when you go up 12 feet. So this would be just fine. And maybe this is a very typical home with recirculation. So again, very, very simple. One PRV will work great for this.
Yep, and you notice that expansion tank down there as well, and yeah, like Kevin said, ensuring that you have that proper set point for ensuring the proper static pressure at the highest point in the system is going to be a necessity.
Right.
All right.
So let's take it up a step.
There we go.
And let's look at a seven floor building. Now here's an example. Again, this is just an example. There are a lot of different ways you can do this. I think the concept is what we're trying to get across here, that if you had a 7-story building and your main pressure coming in was 70 PSI, you could do this that we show here. So again, a couple different ways to do this, but let's say you use the PRV to service floor 0 through 4, so those 5 floors. You can see there that on the bottom level, you would have 45 PSI, which is the setting for your PRV. So 70 in, 45 out. But as you go up, again, there's that subtracting 5, 10, 15, 20 PSI. So you can service more than one floor with one PRV. Now, you have to be aware, again, remember Cody talked about fall off pressure. If you have long runs of piping, you'll get dynamic pressure drops. So those are all things to consider. But in this picture also, you'll notice before the PRV, we come off with a T and are going up to service floor 5, floor 6, and floor 7 before without using the PRV. So you're servicing that mainly with the 70 PSI coming in. And you can do that too. Again, just remember the static head difference between the floors, right? And in this example, we're just showing the blue water service. In this particular example, you would have domestic hot water production for each of those floors. That would be a separate thing. So again, a pretty simple, one PRV for floor. Again, just one of the examples. Okay, go ahead.
Yep.
All right, so let's take it up another level. So let's look at a 10-story building. Now this gets a little more complicated, but if you look at the bottom, let's say we have 70 PSI coming in and we have some booster pumps raising that pressure up to 95 PSI. Now with that 95 PSI, we're pressurizing the tank for the indirect heater and all of the blue piping all the way up to the 10th floor. And also that water heater, the hot red piping coming out is going up to service each of the floors as well. And you can see the pressures, the upstream pressures as you go up. And eventually you're going to get to the point really around floor 8 or 9, you probably don't even really need PRVs, because look at that, we're just directly we have 55, 50, 45 PSI to use up there. So even though we show PRVs, it'd actually be optional up there. Now, the nice thing about this is you have a PRV for the cold line and a PRV for the hot line coming in to the floor. That's actually really good. You get excellent control for each of the levels on this. Now you're going to have to purchase more PRVs, but this is a really solid design if you lay out a system that looks like this.
And a great point to bring up too, Kevin, and I didn't bring it up earlier. All of our pressure reducing valves are rated NSF 61 all the way up to 180 degrees Fahrenheit. So if you are boosting hot and cold water, every single one of our PRVs can handle that, no problem whatsoever. And you can do that in these applications as well. So
yeah, and that's the highest level of NSF 61 is that 180 degree Fahrenheit.
Yep.
All right, let's take it one step further. Here's a 35 floor building. Now we're going to break this one into zones. If you start at the bottom, we have 70 PSI coming in on the mains, and we have a couple of booster pumps that are pumping up to 220 PSI. So what we have to have is that with that heat exchanger that Cody's pointing to there, because you can't put 220 PSI into a typical water heater. So we have to put a heat exchanger in between. And in this case, we have high pressure all up through the riser. So that 220 is going all the way up the building and also on the hot side as well. So now we have this high pressure riser. So you'll notice on floor 0, we have an exploded view there. Here's where we have to do two-stage pressure reduction. If you look at that box on the left, we've got 220 PSI. We're reducing that down to 90 and then to 45. And then that 45 is going to service 5 floors there within that zone box. Okay. Now, again, those numbers are just random, but the point is you can do this with a high pressure riser, put two-stage PRVs up until the point where you get to about floor 20. Now, look, we have 120 PSI in the risers. So now you can just do that with one set of PRVs, right? Because now we're just going to reduce 120 instead of having to reduce 220 or 170 or 195. There from there up, we can just go with a single set of PRVs, and we don't have to do two-stage pressure reduction. Let's see what else to say about this. This is a pretty efficient way to do it because we're using PRVs for each zone. So a set of PRVs is controlling actually 5 floors. It's a pretty efficient way to do it. And again, just remember, these are just single illustrations. There are so many different ways you can do it. I think the concept, though, we can get across.
Perfect. Yeah. And I think one of the things you guys as engineers are probably looking at right now is you're looking at this diagram right here and thinking to yourself, there's no way I can get away with recirculating, from the top back down to the bottom again without going out into the building. Our runouts are getting shorter and shorter and shorter. Most places I'm seeing 2-foot runouts from your circulated lines to your fixtures, and this is obviously not going to fly. And one of the things that you'll notice here is we're boosting to 220 here, going through the heat exchanger. The hot and cold risers are going to mirror each other all the way up as far as pressures, right? But what you also need to remember is that the recirculation line that's coming back down from the top down will also mirror those exact same pressures. And this is another call that we get quite often. And I guess the kind of the golden rule, if I could get you to really nail down anything in this particular little segment here, is that we can never, ever, ever recirculate across the pressure reducing valve. So if we have a scenario like this where you've got to go out into your branches and recirculate back because you can't have those long runouts, how do we do that? Okay. And so the issue here is, and I've just got a simple diagram here. It doesn't matter whether the water, your domestic hot water is coming from the top or coming from the bottom and getting boosted or anything like that. It doesn't matter. Again, those return risers will mirror whatever the domestic hot water distribution is. And what happens here is that, say, for example, at these lower floors, again, doesn't matter if it's coming from the top or the bottom, you're going to be, reducing from, say, that 155 PSI down to 80. Okay, you're going to go out and to hit your fixtures and you're going to bring that back and you're going to have a recirc riser that's going to mirror those same pressures, and you're going to try and take that 80 PSI line and push it back into a line that is 155 PSI. Okay, and the problem here is there's a check valve in there somewhere. Somewhere along the lines, there should be a check valve, right? And in that check valve, you're going to have 80 PSI on one side and 155 PSI on the other side, and nothing's going to want to move. I mean, you're going to have a 70 PSI plus differential. I mean, it's going to take one heck of a circulator to do that, right? And we get calls like this, believe it or not, quite often where they're trying to overcome these kind of scenarios because they don't have, they don't have domestic hot water. They're not getting hot water in those areas because the recirc is taking just so long because it doesn't even work, right? As a quick example, I actually had a hotel that was being worked on by an engineer, for example, and they had so many issues and so many guest complaints that in order to overcome this issue, they just basically opened up a drain on the low pressure side of the PRV, and they were basically dumping like 2 to 3 gallons per minute down the drain just to keep water flowing through, so that way people could get hot water as quickly as they'd expect in a fancy hotel like that, right? And so obviously that is not encouraged. So how do we overcome this? How do we make this recirculation system work without having to go from an 80 psi line into 155 psi line, or whatever the pressures happen to be? And how we do that is typically through a scenario that's similar to this, where you're still going to have the pressure reducing valves to knock down from the high pressure risers to your particular zones that you're serving, right? But instead of bringing that back into a high pressure riser again, you'll notice here we actually have a plate heat exchanger. And this plate heat exchanger, normally you're separating glycol from fresh water, or non-potable from potable water, or whatever the case may be. But in this case, we're using that plate heat exchanger to separate 2 different pressure zones. And what we're doing within that particular pressure zone, whether it's 4, 5, 6 floors in that pressure zone, is that we're treating that like its own system, okay? And you're going to recirculate the high pressure side here from your domestic hot water source through those risers, but downstream of the PRVs, you're going to have your own little system down here, and you're going to have that plate heat exchanger that's circulating on the high pressure side and the low pressure side. You're going to have a thermal expansion tank, and that plate heat exchanger, all it's really doing is maintaining the loop temperature while there's no demand. And so what we're really worried about here as far as sizing this plate heat exchanger is the heat loss through these risers that are out off of the reduced pressure area, right? And so, this plate heat exchanger doesn't need to be terribly big. I have seen some applications where they've used electric water heaters to do this, just like small little electric water heaters. That's kind of a no-go in a lot of areas nowadays because of the need for heat pumps. So if you are looking at heat pumps to do this kind of application instead of a plate style heat exchanger like this, do ensure that you have proper airflow and adequate space for a typical heat pump like that. But this allows you to do recirculation through those reduced pressure areas without having to try and get it back across here into the high pressure risers. So again, this is a golden rule right here. In larger commercial buildings where you are doing pressure zones like this, you cannot recirculate across a pressure reducing valve, because it will never go well. So whether it be with a plate style heat exchanger or with a small water heater to maintain the loop temperature, you can do that no problem and make life easy for yourself. So from there, we're coming to the end here, and I just want to summarize, pressure reducing valves and proper sizing can save your customers money, whether it be with water waste or stress and repairs due to high pressure, or potential failures that cost a ton of money to fix for your insurance company or your building owners. There's a lot of money to be saved here for this stuff. PRVs, very simple devices, and they're very, very reliable, again, as long as they're sized appropriately and they're not all full of debris, right? So from there, sizing them properly will help to prevent undesirable outcomes, or those squealing noises, the chattering noises that we talked about before. If you have a chattering PRV, you'll even see it on the pressure gauge where that needle will just bounce up and down. It's pretty bad on that. It's hard on the diaphragm, and we want to try to prevent that. Pressure reducing valves have maximum and minimum flow requirements. So make sure we're abiding by those minimum flow requirements, and if necessary, do the parallel PRVs in those applications. And we talked about this just a second ago, but parallel and series PRVs can help with flow requirements and high incoming pressures. So if you've got the high flow requirements and the low flow requirements, you can do that with the parallel. If you've got high incoming pressure and you're knocking it down to a ratio greater than 2 to 1, you can do the series PRVs to help handle that as well. But malfunctioning PRVs, it's something that we get quite often on calls. Hey, I replaced this PRV like for like and it still doesn't work. Well, that's not necessarily the way we want to diagnose this, because that could just be a sizing issue. But when it comes to malfunctioning PRVs due to dirt and debris, they are easy to pull apart and clean up and diagnose like that. And then, like I said, we just talked about this a minute ago. Never, ever, 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 ever recirculate across a pressure reducing valve in a commercial building, because it's not going to go your way. So from there, I'm going to hand things back over to Max. We can finish out the slides here. And then we did get a lot of questions, Max. Holy cow, did we get a lot of questions. That's
So
the best one yet.
I've got a couple questions that we can go through. I'll just wrap it up here. So if you want, we have some very specific questions. Reach out to us either by email or this is a direct phone line, so we can get back to you. We had some, down to a specific job site questions from a couple people, so we're happy to follow up there. And then if you have a good use of these products out in the field, we'd love to see those on social media too. So tag us there. We're happy to kind of share the best practices and cool projects that you've put together. One of the questions that we got was on kind of the switch to pilot operated. So what is like a breaking point there? That at some point, if you're looking for 8-inch flanged pressure reducing, are we still in the world of direct acting, or when have we graduated to a different technology there?
Yeah, Kevin, I'll let you steal that one. You're quite the bandit.
Yeah, that's as soon as you get into flanged valves, Max, anything above 2 inches, then pilot operated PRVs are a good idea. They eliminate fall off pressure, and 2 inch, 2.5, 3 inch, that's all going to be flanged, and you're not really looking at direct acting valves at that point for the most part. Some manufacturers do have some flanged direct acting valves, but they're extremely expensive, and at that point I would just go with a pilot operated.
We also had a service question. So the question was, if you have both hot and cold PRVs in a system, do they need to be serviced at different intervals? I don't know that we have anything specific for that, but my guess would be anything very hot, whether it's a mixing valve or a pressure reducing valve, is going to scale quicker. Is that kind of a basic answer to that question?
Yeah, I would have to agree with that. Yeah, I mean, as your temperatures increase, your magnesium and calcium will want to come out of precipitation. Especially if you don't have water treatment of some sort. At that point, I would always encourage, and you probably noticed in some of the diagrams where we had isolation valves on either side. Getting these on some kind of preventative maintenance schedule and having isolation valves so it's easier to take care of them is going to make life a lot easier in that building going forward.
Okay, we're still trying to sort through all the ones that have come in. I'm going to run out of mustaches here before I can get to all these. So we will follow up
You need
with
to turn
everybody.
them into eyebrows. Is
The
what you need to
eyebrow.
do, Max.
Okay.
I see the chops over there.
I'm going to have like a chemical burn from the cheap adhesive in these mustaches by the end of this webinar. So I'll switch to the aging mustache because we're getting close to the end here. Another question at the very beginning was just the reason to use the hot pressure, the hot and the cold, based on the fixtures too. So if you're going to do some domestic hot water strategy that is really a pressure penalty, like maybe a hot water coil through an old cast iron boiler or something where you might have a pretty big delta between the hot and cold, would be very different from some of the other water heating strategies. Do you want to kind of mention that a little bit, why it may be more important depending on the water heater that you're using to reduce cold to match the hot?
Yeah, so at that point too, I mean, if you've got risers or distribution hot and cold that aren't somewhat close in pressure, it will typically have a tendency to exacerbate cross connections in the building because cold, high pressure wants to go to low pressure, hot wants to go to cold, so on and so forth. But in this case, if your cold side is higher, if you have a cross connection in that building somewhere due to foul check valves or a mixing valve somewhere that doesn't have check valves on it altogether, you're creating an uncontrolled mixing scenario, which will mix down your hot side, and you're not going to get your full hot temperature to your fixtures and things like that. So is that what you're kind of going towards there, Max?
Yeah, I think that just in some cases, if you have only a 5 psi penalty across a water heater, it may not even be noticeable at that point versus taking a 25 psi penalty that if you took the single handle faucet and went left to right, you'd notice that it's spraying out of the bowl or it's just drizzling or whatever.
For sure.
And then we've got a couple other code questions too that we'll probably have to follow up with after the webinar here. Do you see anything else, Cody? We've got one about we need to add oh, go ahead.
I was going to say with with whether it be questions in the webinar today or questions that you submitted during registration, there was a lot of them, and there was a lot of great questions in there, and we tried to hit on as many of them as we could. If we don't get to your questions today, we will be in touch, in the near future to kind of go over those with you if there are any questions that were unanswered there. But just to let you guys know. So sorry, Max,
Yeah.
go ahead.
Yeah,
Okay.
between the three of us, we will get answers to all of your questions.
Yep.
I can send you the link to where to buy a $6 12-pack of mustaches.
For anybody that's dying to know.
For anybody that needs that in the next like 2.5 hours before they go to a Halloween party. So with that, I think that we can wrap it up, and we will get back to everybody as mentioned. Happy Halloween, everyone. Have a great day, and we will see you in November to talk about a hydronic topic with separators. So we will see you soon. Thank you.
Bye.
Adios.